When you begin to exercise, a phosphorylation cascade occurs, and phosphorylation permeates throughout the entire cell. So you're going to want catabolic and anabolic enzymes to react differently to this same phosphorylation signal so that you're not building up energy stores at the same time as you're breaking them down. This would be a waste of energy. What I like to think of is you begin to exercise, phosphorylation kicks in. Think of that, and then this next part will make a lot more sense. So if you start to exercise, and then phosphorylation begins, it's going to make sense that this phosphorylation signal induced by exercise is going to activate catabolic enzymes. It's going to activate the glycogen breakdown to release as fuel so you can continue to exercise. And it's going to inactivate anabolic enzymes. It's going to inactivate glycogen synthesis so you're not building up glycogen at the same time as you're breaking it down. If you understand that, then these next two diagrams are going to be a lot more clear because they can get a little bit muddy. Okay, so we'll start with glycogen synthase right here, which is an anabolic enzyme that's going to promote glycogen synthesis. So what happens when you begin to exercise? Your hormones epinephrine and glucagon and norepinephrine go up. They work through secondary messengers here to activate phosphorylase kinase, which is going to drive this reaction that turns glycogen synthase into a less active form. Exercise is going to turn down glycogen synthesis. On the other side of this, exercise through epinephrine and glucagon is going to inactivate protein phosphorylase. So exercise is going to turn down this reaction that creates a more active glycogen synthase. So you begin to exercise and you turn up the inactivation of glycogen synthesis and you turn down the activation of glycogen synthesis. And these work together to just turn down glycogen synthesis. Insulin, an anabolic hormone, is going to act to inactivate phosphorylase kinase. So insulin is going to inactivate this reaction that causes glycogen synthase to be in its less active form. It's an anabolic hormone. It's going to want to build up glycogen, so it's going to inactivate the reaction that deactivates glycogen synthase. Inhibition of inhibition. On the other side, insulin is going to promote, through protein phosphorylase, this reaction that drives the more active glycogen synthase. So it's going to work, again, just like exercise hormones on both sides to have a compounding effect. Now, if we look at a catabolic enzyme, like glycogen phosphorylase, what happens during that exercise-induced phosphorylation? So you begin exercise, your epinephrine, your glucagon, and your norepinephrine shoot way up, and they're going to activate phosphorylase kinase. This is going to drive the reaction that produces a more active glycogen phosphorylase. It's going to upregulate the breakdown of glycogen to be liberated as fuel. So now, onto insulin. Insulin, an anabolic hormone, is going to inactivate phosphorylase kinase, so it downregulates this same reaction that produces a more active glycogen phosphorylase. So insulin, an anabolic hormone, is going to inhibit in a reaction that would produce more glycogen breakdown. It's also going to activate protein phosphorylase, which is going to drive the reaction into a less active glycogen phosphorylase. So again, just like all of the other times, it's going to work on both ends. It's going to inactivate this reaction that produces more glycogen phosphorylation through GPA, and it's going to activate this reaction that will turn down glycogen phosphorylation by turning it into glycogen phosphorylase B, the less active form.